Alright, hey guys. What we're going to do today is just talk about exponential functions. Now, you're going to learn a lot about exponential functions in Algebra 2, but we did already learn some in Algebra 1. So this video is really just meant to refresh our brains about what we learned in Algebra 1 in ninth grade so that we're prepared to build off that for Algebra 2. So, exponential functions have a general form, and you might want to take notes. They have a general form of y equals b or a times b to the x power, where a is the initial value or the starting, and a is also known as the y-intercept, and b is the growth rate or multiplier. So if I were to draw an exponential function on a graph, I know that exponential functions have either dramatic increases, like the blue, or they have very dramatic decreases, like the green. The biggest difference between exponential and linear is that exponential has a constant rate of change. Linear has a constant rate of change, and exponential does not. So to keep in mind that when I talk about a, the starting value, if I were to look at it on this graph here in the blue, I would know immediately that the starting value was right on the y-axis, right on the y-intercept. That's always really important to know about the graphs because it can help you figure out equations a lot faster. I also want to talk about what it would look like in a table. So let's say we had something that started at 2, and then the next couple of x values were 0, 1, 2, 3, and y was 4, 8, 16. You can see here that this is not going up by a constant rate, but it's actually being multiplied by 2 each time. So if I were actually to make an equation like the general form a times b to the x, about this, I would know like, oh, my starting value is when x is 0. A y-intercept is when x is 0. That might be something good to write here. Well, then that means my a value is 2, because when x is 0 here, a is 2. And now I don't know my b, but I know that x is going to remain an exponent. My b is my multiplier. Well, my multiplier here, all I've seen is that every single time x went up by 1, y doubled, or y went up by 2. So in this case, my multiplier would be a 2 as well. Please be sure, this does not mean 4 to the x power. Remember PEMDAS, parentheses and exponents would come first, then that multiplication. So I would first want to make sure that this is not something I write 4 to the x. Nope, it's 2 times 2 to the second power, or 2 times 2 to the x. So in this case, that would be the equation of this table. So this general form we want to keep in mind. The other form, however, that we learned when we were freshmen was when we used percentages. So when the rate wasn't an even number, or we didn't have a perfect multiplier, we have this other form. It's when we use percentages as growth. Well, this is the form that we use. It's y equals still a times 1 plus or minus r to the t or x. We'll just keep it as x. Where r, right here, is actually my rate as a decimal. This is important as a decimal. So we're going to keep this in mind when we go through these problems. All I want us to do in these problems is create equations based on the written scenario. The Regents and SAT loves to make written scenarios and ask you to create the equation, so you just need to be really good with reading and figuring out what information you can take out of it. So let's start with this first one. Start with $1, doubling your money each round you play of cards. Well, that's nice because all I know already is that I started with $1. Well, I also have this keyword doubling. Doubling means going up by 2. I mean, not going up by 2, but being multiplied by 2. So if I'm looking at this original equation, y equals a times b to the x, I know that a is going to be my starting value. Well, I started with $1. My b is my multiplier. In this case, it's doubling, so it's going to be multiplied by 2. I'm done. Moving on. A bacteria losing half of its 65-ounce mass every minute. Okay, well, again, I see that 65 is my starting value, so that goes first. It's going to be multiplied by my growth rate to the x power. But in this case, I'm a little more confused. A bacteria losing half of its mass. Well, I know that half is like 50%. And I'm trying to think of my multiplier here. Well, it's going to go down. It's really like, it's like dividing by 2. And so in that case, I could think about it like this. If I had one whole and I lose half of it every time, what am I going to be keeping each time? Well, this one's really easy. 1 minus 1/2 is 1/2. So every time I lose 1/2, I only have half left. This is what we're going to keep. What am I keeping each time? Well, that is my multiplier. I'm keeping half of it every minute. So that was a little trickier, but half-life is actually something that you're going to see a lot of in bacteria. So we're going to make sure that we're really comfortable with it. But this is my equation. Moving on. There's a population of 4,000 ants that are tripling every year. Okay, well that means starting is 4,000. 4,000 ants to start, tripling every year. Well, tripling is pretty easy as well. If I think of anything tripling, 1, 3, 9, 27, my multiplier here would be times 3. So again, pretty easy stuff. There's my equation. An investment of $600 grows at a rate of 3.5% every year. Great. I have an investment. It starts at 600. It grows at a rate of 3.5 every year. Well, here's the problem. If I put 3.5 in here as my multiplier, that means that $600 is more than tripling every year because of 3.5. And I know that 3.5% definitely does not mean that it's going to be more than 3 times 600. 3.5% isn't that much. So this is where we start to go back and use the percentages equation. So I had y equals a, so what I've set up so far can stay. But then it's times 1 plus or minus r to the x, and it says rate as a decimal. So I'm going to have to erase this, because it's definitely not 3.5. But 3.5 as a decimal, well, I know 3.5%. Percent stands for per 100, out of 100. So 3.5 divided by 100, if you really need to use a calculator, which you definitely shouldn't, but would get you 0.035. But that's confusing to me too, because if I put that in, that means 600 is going to get super small really fast, and I'm going to lose a lot. So I have to remember that my equation said 1 plus or minus the rate. This is because you have to start with your whole, your 1, and you either add or subtract based on what this percent is doing. In this case, we're growing, so I'm going to write plus 0.035. And then this I can combine here. So my final equation should be y equals 600 times 1.035 to the x power. And I'm done. 2 more. Allie just bought beets for $350. They depreciate at a rate of 40% per year. Write an equation to value if Allie's beets after 2 years. I think I meant value Allie's beets after 2 years. Alright, so after 2 years means that I should probably use something like value after t. V of t, well, her beets started at $350. Then they're depreciating at a rate of 40% per year. Now, per year tells me, percent tells me that I should be using the 1 plus or minus r to the t equation. So I'm going to write 1. Depreciation means losing, so like losing the value, which is true. When you buy something like Beats or an iPhone or a car, they immediately become less valuable because they've been used. So I know this is going to be losing this rate of 40%, and then I know that 40% is 40 out of 100, which is equal to 0.4. So 1 minus 0.4 to the, I almost wrote x, to the t power. So the value in terms of time starts at 350, loses 40% every single year. And then I'm just going to combine this here. So V of t equals 350 times 0.6 to the t power. And this makes sense to me because if I'm losing 40% of something every year, then what I'm actually keeping is 60%, 0.6. And so I'm done here. And then finally, putting your $1,200 into a bank account that earns 3% interest each year, how much will you have after 10 years? Well, let's start with an equation. I start with $1,200. I earn 3% interest. Percent means I'm going to use the 1 plus or minus rate. Each year, 3% divided by 100 gets me 0.03. Write it in as my rate. I equals 1,200 times 1.03 to the x power. Now, FYI, guys, if you ever find a bank that gives you 3% interest, find that bank and tell everyone because it's like there's no way. My savings account, I'm pretty sure, gets 0.001% every year. So, excuse me. The question didn't ask us to create the equation. It says, how much will you have after 10 years? So in this case, I know that 10 years means that this x up here is going to be in terms of 10 instead of x because I have a value for time. So all I'm going to do is plug in 10 for the x. And I can literally put this whole thing in my calculator. Don't put the y equals, but here I can put this whole thing in my calculator. 1200, parenthesis 1.03, parenthesis, and then to the power of 10. I push enter. You should get something like 1612 .699 ... Well, I'm talking about money, so I have to cut it off after 2 decimal points because we don't have more than 3 decimals for cents. So $1,612, well, in 69 cents, but then in 9/10 of a cent after that, I'm just going to round it to 70 cents. Again, putting $1,200 into a bank, earning 3% interest, doing nothing with it, and making $400 is pretty easy money. So my answer is $16.12 and 70 cents. Alright, we're going to use a lot of these things and more in class tomorrow and for the next week or so, but I just wanted to give you a quick refresher on what is going on that we have to remember from Algebra 1.